and welcome back. In this video, we're going to look at a couple problems that incorporate gases with stoichiometry. The first one involves something that we studied before with gas laws. It's called the law of combining volumes. And then the second one is going to look a lot like typical stoichiometry problems that we've been doing over the last little while. All right, so let's dive into this first problem. This problem states that we have some propane gas reacting with oxygen via a complete combustion reaction to produce carbon dioxide gas and water vapor. Now, suppose we have 1.5 liters of propane gas and it is completely consumed. It's consumed through this complete combustion reaction. So a few things going on here that I'm going to go into. First off, propane gas reacting with oxygen. This is a reaction that occurs in your barbecue. You have a tank of propane gas, and when you open up the valve and allow the gas to flow through the hoses up into your barbecue, you light the flame, you are burning propane gas. And the barbecue is designed to make sure there's enough oxygen getting in, actually more than enough oxygen than you need. This is where the setting that is required to give you a complete combustion reaction. What this means is that we have lots of O2. We've got lots and lots of O2. So more than we need to be concerned about. So we've got this reaction with propane, with oxygen making carbon dioxide gas and water vapor. The questions are, what volume of oxygen gas is consumed if this is how much propane we consume from the tank? And then the follow-up question is, how much carbon dioxide gas did I produce? So let's start off with our balanced chemical equation. So I would encourage you to pause the video here and write it out and balance it. Otherwise, I'm going to keep going. And in order to balance this, I need to have 3 carbon dioxide molecules, I need 4 water molecules, and 5 of those. Does that make sense? Yep, I think I got everything. 3 carbons, 8 hydrogens, 8 hydrogens, 10 oxygens. I get 6 oxygens from the carbon dioxide and 4 from the water, which adds up to 10 on the right. So this looks good to me. Okay, so I've balanced it. I can start answering question A. What volume of oxygen gas is consumed? So as I said, this has something to do with the law of combining volumes. I included a statement in here that says the propane and the oxygen are at the same temperature and pressure. And what the law of combining volumes states, it's an offshoot of Avogadro's law, but it says equal volumes of gases at the same temperature and pressure will contain equal numbers of moles of gas. So the handy thing about that law is that I can actually take these coefficients to tell me moles of gas, or they can also just tell me volumes of gas. Since all these chemical components are at the same temperature and pressure, I can either treat these coefficients as telling me a mole ratio or a volume ratio. So, what volume of oxygen gas is consumed? Volume of O2 that's consumed in this reaction? Well, I start with 1.5 liters of propane, and here's where I'm going to use the mole ratio. Or, since it's the law of combining volumes, I can use this volume ratio, but it's going to be the same thing. It's because we're just using the coefficients. So how many liters of O2 are consumed for every 1 liter of propane? Well, I consumed 5 liters of O2 for every 1 liter of propane. And notice my conversion factor here. I'm using unit analysis. I start out with the unit I have with the measurement, and then in my conversion factor, I put the unit I want on the top. So I want liters of O2. I have liters of propane. So liters of propane are going to cancel out when I perform the calculation. And my final unit will be liters of O2, which is what I'm looking for. I'm looking for a volume of O2. So what do I do here? I do 1.5 times 5, which gives me 7.5 liters of O2. There you go. When you consume 1.5 liters of propane from the propane tank, this requires 7.5 liters of O2 to be consumed. All right, follow-up question. What volume of carbon dioxide gas is produced? Okay, so very similar. We're just going to use a different ratio. So here we're going to ask ourselves, how much CO2 does this reaction make per 1 liter of propane? Or rather, how many liters of CO2 does this reaction produce for every 1 liter of propane? Since these are occurring at the same temperature and pressure, I can use Avogadro's law to say here that equal volumes have the same number of moles. So what this means, 3 liters of CO2 per every 1 liter of propane. There we go. So it's the same kind of thing. Liters of propane will cancel out, and my final answer will be liters of CO2. So I get 4.5 liters of CO2. All right, that's that question done. I'll see you in the next video. We're going to do another example of a gas stoichiometry problem.